Mr. Myas is here. Hey guys, and we're looking at 4-2 today, which is increasing and decreasing functions and using what we call the first derivative test to find relative extrema. So we're going to see if I can fit this in one video this time. Hopefully it's not too long, but we're going to take a look. And again, one more time, this is for Essentials of Calculus, but hey, let's get into it, guys. So we got to take a look at what we did in the previous section 4-1 where we found the critical numbers. So to find the critical numbers, we are going to take the derivative, set it equal to 0, and find any critical numbers. Then what we're going to do is we're going to add one more step to this, and we're going to put a number line for f prime. Ooh, that was kind of cool. I did it with my hand magic. We're going to do a number line for both the domain restrictions of f prime and the domain restrictions for f, and also the critical numbers. And then we're going to use that number line to see where the intervals that the sign of f prime is either positive or negative. Where the sign is positive, then that means it's increasing. When the sign is negative, it means it's decreasing. And where we have those that increase and then decrease, that's a relative max. Decrease, then increase, we've got a relative min, and we'll go in and label those if requested. So let's go and take a look at some examples here. Find the intervals in which each of these functions are increasing and decreasing, and then we'll find the extrema. All right, so let's start with number 1. And so the first thing we look at is the domain. Are there any domain restrictions? Well, the domain is all real numbers in this case, so no domain restrictions. Okay, so we got all real numbers. So let's go and take the derivative. So f prime of x is 2/3 times x squared minus 9 to the negative 1/3 times the derivative of the inside. We don't want to forget our chain rule. All right, so that's going to look like 4x over 3 cube root of x squared minus 9. So now we've got to find our critical numbers. Well, our critical numbers are going to be when f prime of x is equal to 0. So when is f prime of x equal to 0? So we got x equals 0. Well, that's pretty much it, right? We take the numerator and put it equal to 0. Okay, do we have any places where f prime is undefined? Undefined. Do we have anywhere where that exists? Yes, they're right here, the denominator, right? So x can't be equal to plus or minus 3. So x is undefined at x equals plus or minus 3. So these are our critical numbers. So what we're going to do is we're going to make a number line, an f prime number line, and we're going to plot our critical numbers, 3, 0, and 3. Now what I like to do on the ones that are undefined, I like to just kind of put a little dash here, because I know that there it's going to be undefined. And it's not a vertical asymptote, but it's undefined for our f prime. Okay, so now we're going to test out a number. So all we're going to do is we are going to take a number in here, like negative 100, and we're going to plug it into our f prime, and we're going to see if it gives us positive or negative. So when we do that, we're going to get negative on top. The bottom is going to remain the same. So no matter what I put in for the denominator, it's going to be positive. So this is going to be negative. If I put a negative, like a negative negative 2 in here. All right, that negative 2. Actually, this is a cube root, not a square root. So the bottom doesn't always have to be negative. Negative 100 is going to give me a very large number, right? So that's going to be positive down here. A negative 2, actually, let me use a negative 1. Negative 1, however, is going to give me 1 minus 9, which is a negative value. And when I cube root a negative value, I still get negative. So I'm going to get a negative divided by a negative, which is a positive. When I put a positive 1 in here, I'm going to end up with a positive divided by a negative, which is going to give me a negative. And then when I put a big number like 100, I'm going to get a positive. So what does this tell me? That tells me that on my f curve, all right, so this tells me on my original function f, I'm going to decrease, and then it's going to increase, decrease again, and then increase there. So now I know the intervals in which it increases and decreases. So I'm going to say it increases from -3 to 0, and then again from 3 to infinity. It's going to decrease from -infinity to -3, and then again from 0 to 3. We have relative mins. Where are our relative mins? Well, here's a min here, and here's a min here. So I have a relative min at -3 and +3. What's that point? If I plug 3 back in here, use blue for this so we're not confused. If I plug 3 back in here, it's going to be 9 minus 9. That's going to give me 0. Okay, so my relative min is going to be at ±3, 0. And my relative max is going to be right here at my x equals 0. 0, 0, we'll just put -9 to the 2/3. All right, there's my relative min and max. Here's my increasing, decreasing, and there we go. Okay, so that's basically the way we're going to do all of these. We're going to take the derivative, set equal to 0, find our critical numbers, and then now we're just going to test to see where we're increasing or decreasing based on whether it's positive or negative in the derivative. Okay, so that's why I have a derivative number line here. It looks like a Christmas tree. It's red and green. And then I have my f, my corresponding f, what's going on when it's increasing and decreasing. Let's take a look at a couple more examples. All right, number 2. So we already know that our domain x cannot be equal to 0 there, right? So that's going to be one of our critical numbers when we take a look at that. Ooh. So now we'll do the derivative. Oh, such a long derivative. So I'm gonna do low-d high, high-d low here. I've simplified it here for you. Oops. And what I'm going to do now is find out when is my f of x equal to 0. So f of x is equal to 0 at x equals 1 and x equals +1. So I'm just taking the numerator here and setting equal to 0. Then I also know that f prime is undefined at x equals 0. I get that from my right here, my domain, and plus it's in the denominator there. Since it's undefined at x equals 0 because the derivative doesn't exist, there's like nothing, right? It's an asymptote to start with. Okay, I'm just going to put that this is a vertical asymptote. It's not a critical number. These are my only 2 critical numbers. So, but I still got to deal with it on my table. So I'm going to do my f prime table here, and I've got -1, 0, 1, and I'm going to put like a little more of a vertical asymptote there to show that that's a vertical asymptote at x equals 0. I have my line. Okay, right there. Vertical asymptote. All right, now we're going to test it. Test it, testing. So negative, we'll use negative, like -30. It doesn't really matter. But when I put this big negative number in here, I'm going to have a positive. A negative make a positive. Divided by a positive is all going to be positive. If I put like a -1/2 in here, I'm going to have a positive here, a negative, a positive, which is going to make a negative, and a positive, which is going to make negative. So I don't need to know what the actual number is going to be. I just need to know whether it's positive or negative. So just keep that in mind. So when I'm going through this and you're like, what's he doing? How's he getting that? I'm just finding out if it's going to be a negative or a positive. I don't really need to know the actual value when I plug in these things. So if I put in like 1/2, 1/2 is going to give me a positive here. It's going to give me a negative here, a positive here, which makes it negative, and then still positive on the bottom. So this is still going to be negative. And then if I put a big number here, I'm going to end up with a positive. So this looks like this now for the f graph. Up, down, decreasing, decreasing again, and then increasing. Oh, that's interesting. Well, I got an asymptote, so it's likely this is going to go down like that and up like that. But you know what? It wasn't asking me for that, so I'm just going to go ahead and answer the question. So where is it increasing? Well, it's increasing on the interval from negative infinity to negative 1, and then again from 1 to infinity. It's decreasing on the interval from negative 1 to 0, and then again from 0 to 1. Well, let's see. I do have a relative max. My relative max is at negative 1. Now plug in negative 1 in my original function. I'm going to get 4/3. And I do have a relative min right here. So I'm going to plug 1 in to my original function, and that's going to give me, oops, this should be a negative. This should be a positive. All right. Okay, so there was another example. This time it had a vertical asymptote. So I'm going to do one more example here to try to get through one more type that's kind of neat here. We got a polynomial. So we're going to first, again, we're going to take the domain. And the domain for a polynomial is all real numbers. All right, pretty simple. Who's the realest function in the room? The polynomial. Yeah, never mind. We're going to take the derivative now. 3x squared minus 6x plus 3. And we're going to set that equal to 0. All right, so set that bad boy equals 0. We're going to have 3x minus 1 squared equals 0. So f prime of x equals 0 at x equals 1. And then there's no place where f prime is ever undefined because, well, I've got a polynomial. So that's kind of nice. So we only got one critical number. Woohoo! Critical number at x equals 1. You're like, wow, I thought you were going to put the hardest one at the end. I don't know, guys. That's why math is so interesting. You never know what's going to happen. F prime. When I plug in 0, I'm going to get positive. And when I plug in 2, I'm going to get what? What? Positive, positive. That means it increases and then increases again. No change in slope, or no change in increasing or decreasing. See, I told you it was going to be interesting. You never know what's going to happen. Okay, increasing. So we're going to increase to infinity and beyond, like Buzz Lightyear. And we're never going to decrease. And there's no relative extrema. So what's going on? Well, this is just going to keep going up and up forever. So this is called a monotonic function. Monotonic meaning that it is strictly monotonic. It only either always increases or always decreases. All right. So this problem itself illustrates two really important things. One, that not every critical number produces a relative min or a relative max. Sometimes it just is what it is there. And then even though the slope at x equals 1 is 0, the function's still always increasing. So what's going to happen is essentially this is just going to have a tangent line that's 0. Right? It's going to go like this, and then it's going to continue to increase. So this is always increasing, even though the slope there is equal to 0. All right, guys, so there we go. We've got the first derivative test. That's how we use the first derivative test. We take the derivative, find the critical numbers, and use some sign tables here on number lines to determine where the function is increasing or decreasing. All right, guys, we'll catch you next time. Later.